Welcome to Section 1, Lesson 4. Today we look at Exponent Rules, Part 1. Exponents are how mathematicians compress repeated multiplication into a single short notation, the same way multiplication itself compresses repeated addition. By the end of this lesson, you will know the three rules that handle every exponent expression involving multiplication, and you will be able to simplify expressions that look complicated into single clean answers. First idea on the board. An exponent counts how many times the base multiplies itself. 2 cubed means 2 times 2 times 2, which equals 8. 3 to the fourth means 3 times 3 times 3 times 3, which equals 81. The little number written above the base is called the exponent or the power, and the number being multiplied is called the base. Once that meaning is solid, every other exponent rule follows from it directly. Second idea, when you multiply two powers of the same base, you add the exponents, you do not multiply them. So x squared times x cubed equals x to the fifth power, not x to the sixth. The reason is geometric, not magical. X squared expands to 2x factors, x cubed expands to 3x factors, and the total count of x factors in the product is 2 plus 3, which equals 5. We will see this expanded out step by step in the concept seen. When you raise a power to another power, you multiply the exponents, you do not add them. So x squared all raised to the third power equals x to the sixth power, not x to the fifth. The reason again is geometric. Raising to the third power means 3 copies of x squared multiplied together, and each x squared is 2 factors, so the total is 3 times 2 equals 6 factors of x. Two rules, two opposite operations on the exponents, both of them inevitable from the definition itself. Here is the formal definition of an exponent. 2 cubed equals 2 times 2 times 2, which equals 8. The base is the number 2 and the exponent is the small number 3 sitting up to the right. Read the notation as 2 multiplied by itself 3 times, no more, no less. The single number 8 on the right is what the entire expression evaluates to once you carry out the multiplication. Now look at what happens when we multiply two powers of the same base. 2 squared times 2 cubed expands to the open parenthesis 2 times 2 close parenthesis multiplied by the open parenthesis 2 times 2 times 2 close parenthesis. That is 2 factors of 2 on the left grouped with 3 factors of 2 on the right, which gives a total of 5 factors of 2 when written all together. So the answer is 2 to the fifth power. Generalizing the previous example gives the product rule. For any base x and any exponents a and b, x to the power times x to the b power equals x to the power of a plus b. The exponents add up, the base stays the same. This works for any real number exponents, even when the exponents are fractions or negative, which we cover in Part 2. Now look at the second rule, raising a power to another power. The expression open parenthesis 2 cubed close parenthesis squared means 2 cubed multiplied by 2 cubed. Each 2 cubed is 3 factors of 2, and we have 2 copies of that group, so the total count of 2's in the product is 3 plus 3 equals 6. So the answer is 2 to the sixth power. Generalizing, that gives the power of power rule. For any base x and any exponents a and b, the expression open parenthesis x to the a close parenthesis raised to the b power equals x to the power of a times b. The exponents multiply, not add. This is the rule that catches the most students, because the visual pattern of two stacked exponents looks like it should add, but the geometry forces multiplication. And the third rule, power of a product. For any bases x and y and any exponent, open parenthesis x times y close parenthesis raised to the power equals x to the power times y to the power. The exponent distributes to every factor inside the parentheses. Quick numeric check, open parenthesis 2 times 5 close parenthesis squared equals 2 squared times 5 squared, which equals 4 times 25, which equals 100. The same answer comes out either way, because the exponent simply gets handed to each factor. Here is our first worked example. The expression at the top reads x to the fourth power times x cubed times x squared. Three groups of x raised to different powers, all multiplied together, all sharing the same base x. We are going to apply the product rule from the concept seen to collapse this into a single power of x. Step 1. Identify what we have. The same base x appears 3 times, each with its own exponent. The exponents are 4, 3, and 2. Because the base is the same in every group, we are in the exact situation the product rule was designed for, and we can collapse all three groups into a single power of x. Step 2. Apply the product rule by adding all three exponents in the same exponent slot. The expression simplifies to x to the power of 4 plus 3 plus 2. Notice how the multiplication signs between the original three groups disappear and become plus signs inside the new combined exponent. This is exactly what the product rule does every single time. Step 3. Carry out the addition inside the exponent. 4 plus 3 is 7. 7 plus 2 is 9, so the new exponent is just 9, and the expression simplifies to x to the ninth power. Step 4. Display the full simplification on one line. X to the fourth times x cubed times x squared equals x to the ninth. The original expression and the final result, joined by a single equal sign, makes it easy to see at a glance what the rule did to the expression. So the answer is x to the ninth power. Two takeaways from this example. First, the product rule scales up cleanly to any number of groups, not just two. As long as every group shares the same base, you add all of their exponents into a single power. Second, the order of the exponents inside the addition does not matter, since addition is commutative and associative. So you can add them in any order that is comfortable for you. Here is the second worked example, which uses all three multiplicative exponent rules in the same problem. The expression at the top reads open parenthesis 3x squared close parenthesis cubed times x to the fourth. We have a power of a product on the left sitting next to another power of x, and we have to combine all of it into a single clean expression. Step 1. Apply the power of product rule to the left chunk. Open parenthesis 3 times x squared close parenthesis cubed distributes the cube to every factor inside, giving 3 cubed times open parenthesis x squared close parenthesis cubed. The constant 3 picks up its own cube, and the variable factor x squared picks up its own cube as well. Step 2. Apply the power of power rule to the x squared raised to the third power. The two exponents multiply 2 times 3 equals 6, so x squared cubed simplifies to x to the sixth power. The full expression now reads 3 cubed times x to the sixth times x to the fourth. Step 3. Compute the numeric part. 3 cubed equals 3 times 3 times 3, which is 27. So the expression now reads 27 times x to the sixth times x to the fourth. Only the variable parts of the expression remain to combine. Step 4. Apply the product rule to the two powers of x. The same base x appears twice with exponents 6 and 4. The product rule says add the exponents, giving x to the power of 6 plus 4. Step 5. 6 plus 4 equals 10, so the expression simplifies all the way down to 27 times x to the 10th power. Three different rules applied in sequence, one rule per step, each one removing exactly one piece of structure from the original expression. So the final answer is 27x to the 10th. The big takeaway from this example is the chaining pattern. When an expression contains multiple operations, you can usually apply one exponent rule at a time in the order that makes the expression simplest at each step. Power of product first to break apart the parentheses, power of power second to flatten any stacked exponents, and finally product rule to combine same base groups. Three exponent mistakes that catch almost every algebra student when they first apply the rules. Each one looks plausible at first glance, and each one comes from confusing one rule with another. We go through them one at a time, with the right way to think about each one. First mistake: a student multiplies the exponents when they should be adding. They write x squared times x cubed equals x to the sixth because 2 times 3 is 6. That answer is wrong. The product rule says add the exponents when the bases are the same. So the correct answer is x to the fifth because 2 plus 3 is 5. The visual cue is the multiplication sign between the two groups, which signals the product rule, which means addition of exponents. Second mistake. A student adds the exponents when they should be multiplying. They write x squared all cubed equals x to the fifth because 2 plus 3 is 5. That answer is wrong. The power of power rule says multiply the exponents when one power is raised to another. So the correct answer is x to the sixth because 2 times 3 is 6. The visual cue is the outer exponent on a parenthesized power, which signals power of power, which means multiplication of exponents. Third mistake. A student tries to combine x squared and x cubed when they are added rather than multiplied. They write x squared plus x cubed equals x to the fifth. That answer is wrong, and there is no exponent rule for the sum of two powers in general. The expression x squared plus x cubed cannot be simplified further unless x has a specific value. The visual cue is the plus sign between the two groups. Addition of powers does not collapse into a single power, ever. Exponents are not abstract algebra. Every time something multiplies repeatedly, exponents are doing the bookkeeping. Here are 4 real-world places where exponent rules and the product of powers pattern show up directly, often with the rules from this lesson hidden inside the formulas. First, compound interest. The balance in a savings account after n compounding periods is the starting principal multiplied by the quantity 1 plus r, all raised to the n power. The exponent n counts how many times the growth factor multiplies in. 2 years of monthly compounding is 24 periods, so the exponent is 24. The product rule from this lesson is what lets a banker simplify 2 consecutive interest periods into 1 combined period. Second, computer storage. 1 kilobyte is 2 to the 10th power bytes, which equals 1024. 1 megabyte is 2 to the 20th power. 1 gigabyte is 2 to the 30th power. Each step up the storage ladder multiplies the previous by 2 to the 10th, so a megabyte is a kilobyte times 2 to the 10th, and a gigabyte is a megabyte times 2 to the 10th, exactly the product rule in action. Third, earthquake magnitude. The Richter scale is logarithmic, which means each whole number jump represents 10 times more shaking energy. A magnitude 6 earthquake releases 10 to the second power, or 100 times more energy than a magnitude 4. The exponent is the magnitude difference, and the base is 10. Exponent rules are the only practical way to compare wildly different earthquake magnitudes. Fourth, bacterial growth. A culture of bacteria that doubles its population every 20 minutes will multiply by 2 to the n power after n doubling periods. After 10 doublings, the population is 2 to the 10th or 1020, 4 times the original. The exponent counts how many doublings have happened, and the product rule lets a microbiologist combine the growth from 2 consecutive observation windows into 1 combined exponent. 3 things to take with you from this lesson before we move on to the next one. Each one will come back many times in later sections, especially in factoring and in the rest of the polynomial chapter, where simplifying products of powers shows up in nearly every problem. First, when you multiply 2 powers of the same base, add the exponents and keep the same base. X to the a power times x to the b power equals x to the power of a plus b. The plus sign in the new exponent is the rule. Whenever you see same base groups multiplied, the plus sign goes between their exponents inside the result. Second, when you raise a power to another power, multiply the exponents and keep the same base. The expression open parenthesis x to the a close parenthesis raised to the b power equals x to the power of a times b. The multiplication sign in the new exponent is the rule. Whenever you see one power raised to a second power, the times sign goes between their exponents inside the result. Third, when you raise a product to a power, distribute the exponent to every factor inside the product. The expression open parenthesis x times y close parenthesis raised to the power equals x to the power times y to the power. Each factor inside the parentheses gets its own copy of the outer exponent. Coming up next, the lesson called Exponent Rules Part 2, where we cover the rules for division, the zero exponent, and negative exponents.